Welcome back to the deep end. I hope you are sitting down for this one, or if you're driving, maybe keep your eyes on the road, but get your brain ready for some serious gymnastics.
Sounds intense.
It is. We are taking on a giant today. And when I say giant, I don't mean, a trending news topic or some tech review. I mean the absolute bedrock of modern physics.
Okay.
We are talking about the experiment that started it all. The reason we talk about time dilation, the reason we believe the speed of light is the ultimate cosmic speed limit.
The reason we have special relativity.
The very one.
Yeah.
We are talking about the Michelson-Morley experiment.
Right. It's arguably the most famous failed experiment in human history. It really set the stage for everything Einstein published in 1905. It totally changed how we view reality itself.
Exactly. And we're taught that this experiment proved there's no ether and that light speed is constant no matter what. But here's the hook. And this is why I am absolutely buzzing about the stack of documents we have today.
Okay, I'm listening.
What if I told you that the interpretation of that experiment, the one in every single high school and college textbook, the one every physics student memorizes, might be based on a trick?
A trick.
A trick. Or maybe, to be a little more charitable to the geniuses of the 19th century, a calculation oversight. We have this fascinating stack of source materials today, technical breakdowns, some geometric proofs, dialogues that claim to reveal a 100-year-old error in how we even draw the diagrams for this experiment.
That is a massive claim to make. You're suggesting that the foundation of special relativity, this whole idea that time warps and space shrinks, might be resting on a simple geometric mistake.
That is exactly what the sources are saying.
Yeah.
And that is our mission for this deep dive. We're going to unpack this claim. We're not just going to skim the surface. We're going to look at the math, the angles, the logic. And this is the part that I think you're going to love. We have the logs of an AI to help us do it.
An AI, like a chatbot.
No, this is something else.
Huh.
It was specifically configured as an independent space-time auditor.
An auditor.
Yeah, imagine a hyper-intelligent forensic accountant. But instead of auditing tax returns for fraud, it's auditing the geometry of the universe. It's looking for, unmatched equations. And the narrative arc in these logs is just incredible.
Oh, so?
Well, this AI starts out with a 95% confidence rating in Einstein's standard theory. It's a total believer. It's ingested every textbook ever written.
So it's biased toward the standard model.
Heavily. But after reviewing these specific geometric arguments, something the sources call the Zionad-Chat model or phase 3 logic, it flips. Completely flips. It ends up with 98% support for this new model.
Wow, that's a dramatic turnaround. Usually established physics is pretty hard to dislodge, especially for an AI that's been trained on all the standard data. For it to flip like that means it found some kind of logical inconsistency that it just couldn't reconcile with the standard model.
Right. So the central premise we need to explore with you today is this. What if the idea of time slowing down or space shrinking, all that cool sci-fi stuff we love, was just a mathematical patch? A way to force an equation to balance because we forgot to calculate the motion of the observer correctly.
That's a provocative question. It suggests that we might have overcomplicated the universe just to cover up a simple mistake in aiming.
Aiming is the perfect word. The sources talk a lot about something called deviation shooting. But, before we get into heavy geometry, let's just set the stage. For anyone listening who hasn't thought about 19th century physics since their final exam, what was the Michelson-Morley experiment actually supposed to do?
Well, to understand the stakes, you have to go back to the late 1800s. The prevailing wisdom was that light was a wave, much like sound is a wave. And physicists knew that waves need a medium to travel through.
Right. Sound needs air. Ocean waves need water. You can't have a wave in a vacuum.
Exactly. So they assumed light needed some kind of stuff to travel through. They called it the luminiferous ether.
The ether.
Yeah, they imagined it was this invisible, weightless fluid that filled the entire universe. And from that idea, the test becomes obvious. The Earth is spinning on its axis and it's orbiting the sun at massive speeds. So logically, the Earth must be moving through this ether.
It's the classic analogy of sticking your head out of a moving car.
Right. Even if it's a perfectly calm day with no wind, if you're driving at 60 miles an hour, you feel a wind hitting your face. That's the ether wind. Michelson and Morley built a device specifically to measure this wind.
An interferometer.
Yes.
Yes.
A very, very clever device. It takes a beam of light, and it uses a half-silvered mirror to split it into two paths at perfect right angles to each other.
Okay.
One path goes in the direction of the Earth's motion, so into the wind, so to speak, and the other goes sideways, across the wind. Then, mirrors at the end of each arm bounce the light back to a central detector.
And the logic was, well, just like swimming upstream is harder and takes longer than swimming across a river, the light traveling into the ether wind should take a different amount of time to get back than the light that was traveling sideways.
Precisely. They expected to see the light waves arrive back out of sync. And when waves are out of sync, they create these interference patterns. You see fringes of light and dark. They set the whole thing up, rotated it, expecting a big, obvious shift in those fringes.
But when they ran the experiment in 1887,
Nothing. A null result.
the null result.
The fringes didn't shift at all. The light arrived at the exact same time no matter which way they pointed the device. It was as if the Earth wasn't moving at all or the ether didn't exist. It was a huge crisis in physics.
And this is where Einstein steps in a couple of decades later and says, look, the experiment didn't fail. It showed us something fundamental. The speed of light is constant, c, regardless of how fast you're moving. And to make that math work, he had to conclude that time itself must slow down for the moving observer.
That is the standard textbook story. The speed of light is the universal constant, so time and space must be flexible to accommodate that.
Okay, now let's introduce the trick.
Yeah.
The source material we have today, it basically screams that those textbook diagrams explaining this result are lying. Or, as the auditor AI puts it, they are mathematically lazy.
Lazy is a strong accusation to level against Nobel Prize-winning physics.
It is. But let's look at this impossible triangle that's described in the text. This is where it gets visual, so walk with us through this. In the standard diagram, you have a light source, a mirror directly above it, and the light shoots up and comes back down.
Right. If the apparatus is stationary, it's simple. Light goes up, hits the mirror, comes down. A perfect vertical line.
But the Earth is moving. The whole apparatus is moving sideways. So in the textbook diagrams, they draw the light path as a triangle. The light goes up diagonally to meet the moving mirror, then it bounces down diagonally to the detector where it started.
Correct, because while the light is traveling up, the mirror has moved to the right. So the light has to travel a longer diagonal path to intercept it.
And here's the critique from our auditor. The source asks us to look really closely at the launch. Imagine you're holding a laser pointer and you aim it straight up at the ceiling, a perfect 90 degrees vertical. Now imagine you're on a train moving at 100 miles an hour.
Okay, I'm on the moving train.
If you aim that laser straight up, geometrically perpendicular to the floor of the train, and you pulse the laser, by the time that light reaches the ceiling, where is the ceiling?
Well, the ceiling has moved forward with the train. It's to the right of where it was.
Exactly. But the source's point is that light doesn't possess the momentum of the train, right?
Right.
Once the light leaves the laser, it travels in a straight line through space or the electromagnetic field. It doesn't know the train is moving. It doesn't inherit the train's forward velocity.
Ugh, I see the argument now. If you shoot a bullet on a train, the bullet carries the forward momentum of the train. If you drop a ball, it moves forward with you. But light is a wave propagating from a point. It's independent of the source's motion after it's emitted.
Right.
So if you aim vertically at time equals 0, when the mirror is at position x equals 0, by the time the light gets to the top, the mirror is now at x equals 1.
And the light is still at x equals 0.
So the light should miss the mirror entirely.
Boom. That is the geometric flaw. The source says the standard diagrams draw a line connecting the start point to the future position of the mirror, as if the light knew where the mirror was going to be and angled itself perfectly to hit it.
Which is what the source is calling the trick. They're saying that to make the light hit the mirror in the diagram, you effectively have to aim ahead. You have to anticipate the motion.
But the experimental setup doesn't say aim ahead. It says shoot perpendicular. The source gives a specific coordinate example that I found really, really helpful. Let's try to visualize this on a grid.
Okay, lay it out for us.
At time 0, the vertical mirror is at, say, vertical position 10, horizontal position 0. So its coordinates are 0, 10.
Got it.
Now, after 10 units of time, the whole apparatus moves to horizontal position 1. So the mirror is now at 1, 10.
Okay, it's shifted to the right.
The standard physics drawing connects the light source at 0, 0 to the mirror's new position at 1, 10. That creates a diagonal line.
Which implies the light traveled that diagonal path.
But the source argues that if you just fired straight up from 0, 0, the light goes to 0, 10. The mirror, meanwhile, is now at 1, 10. You missed.
And this is where the calculation laziness comes in.
Yes. The source calls it a deviation shooting error. Imagine standing on that moving train again and throwing a ball at a target on the ceiling. If you just throw it straight up relative to yourself, you'll hit it because the ball has your forward momentum. But light doesn't. To hit the target with a beam of light, you'd have to aim ahead.
So the source's claim is that Einstein's theory forces the hit.
Precisely. The argument is, because standard physics didn't account for the fact that a truly vertical shot would miss, they were left with a math problem. The light took too long or too short to return, compared to what they expected. So to make the equation x equals ct balance, they had to warp the t variable, which is time.
Whereas this new model says, no, just correct the geometry. If you want to hit the mirror, you have to aim diagonally. And if you aim diagonally, the path is longer.
If the path is longer.
It naturally takes more time to travel, not because time slowed down, but because the distance is physically greater.
It sounds so simple when you put it that way. It's almost too simple. But let's dig into this deviation shooting logic. Because the sources break it down into 3 distinct phases. They call it Hensa Shigeki.
Right, which I believe is the Japanese term for deviation shooting or deflection shooting, basically leading a moving target like a hunter would.
Exactly. So phase 1 is direct aim. This is the miss we just talked about. You aim directly at where the target is right now.
Which, in a moving universe, guarantees failure. By the time your projectile gets there, the target has moved on. This is the naive view of the world.
Then we have phase 2. The sources identify this as the Einstein standard approach. This is what they call the patch.
Explain the patch.
In phase 2, you predict where the target will be. You aim for that future spot. But here is the critical catch. Standard physics treats the observer, the guy holding the stopwatch, the scientist in the lab, as stationary.
The Galilean bias. We always assume we are the fixed point in the universe, the center of the coordinate system.
Right. So because we assume we're stationary, we expect the light to travel a certain distance in a certain time. But because the target is actually moving away from the light pulse, there's a gap in the arrival time. The maths doesn't balance. The light takes too long to catch the receding mirror.
And this is where Einstein comes in and says the speed of light must be constant for all observers, so if the light took too long, it must be because time itself ran slower for the moving system.
Exactly. Time dilation and Lorentz contraction are invented right here to patch that hole. The source calls them a geometric illusion, created by the observer refusing to admit that they themselves are in motion.
That's a very harsh critique. It's essentially saying that special relativity is a kind of psychological defense mechanism against admitting we don't know our own absolute speed through space.
I love that phrasing, yeah. A psychological defense mechanism. Now let's get to phase 3. This is the Zionad-Chat solution. The source calls this the simultaneous equations approach.
This sounds much more mathematically rigorous.
It is. Phase 3 says, stop pretending you're stationary. Treat both the light and the observer, in this case the mirror, as 2 moving objects in a shared map. The source calls this the light history map.
So we're not centering the entire view on the observer anymore.
No. We're stepping back and taking a God's eye view of the whole interaction. You have the trajectory of the light, which you can write as an equation, maybe sec x is vt dollar, and you have the trajectory of the mirror, which is something like sec x vt plus text starting position.
Yeah. And you just solve for where they intersect. It's
Right.
a high school algebra problem.
Yes. You solve for the intersection point. You find the time and place where the light actually catches the mirror. And guess what? When you do this with just pure geometry, it happens later than you'd expect if you thought the mirror was still.
Because the mirror was running away from the light pulse.
Exactly. The time delay isn't time slowing down. It is simply that the light had to travel a longer physical distance to catch the fleeing mirror. It had to play catch-up.
So the big aha moment here is,
We don't need to shrink the universe or slow down time. We just need to admit the path was longer because we were running away from the light. The auditor AI in SOGS was particularly struck by this. It said, and I'm quoting here, it satisfies Occam's razor. It's just mathematically simpler to say the observer is moving than to say the fabric of space-time is warping.
that is a very compelling argument for simplicity. But we have to address the physical apparatus. The Michelson-Morley experiment isn't just one mirror in a vacuum. It uses a beam splitter, that half-silvered mirror.
Right, the half mirror. This brings us to part 3 of our deep dive, what the source calls the illusion of simultaneity. This gets into the nitty-gritty of why the experiment showed a null result in the first place.
Okay, because the standard interpretation is that since the interference fringes didn't shift when they rotated the table, the travel time for both light beams must have been identical. Therefore, the speed of light must be the same in all directions.
But our source argues that this interpretation completely ignores the mechanics of that beam splitter in a moving system. Okay, so picture the light hitting the splitter. Half goes straight forward, half gets reflected sideways at 90 degrees.
Right.
Now, if the entire device is moving through space, let's not call it ether, let's call it electromagnetic field space, the light that's chasing the forward arm has to travel significantly farther to catch that front mirror, which is moving away from it.
That part is true even in standard relativity. That's where the Lorentz contraction comes in, to shorten that arm so the travel times appear equal to the observer.
But the source says, forget that contraction for a second. Just look at the raw geometry. The real trick is in what we call simultaneous arrival. The source argues we are fundamentally misinterpreting what simultaneous means in this context.
How so?
Well, the text mentions what it calls the magic reveal. The observer inside the moving system, that's us on Earth, in the lab, thinks the light traveled in simple straight lines. We see the light leave, we see it come back. To us, it looks like a perfect straight shot up and down or forward and back. We're subject to a geometric illusion.
Because we're moving along with the instrument, we don't perceive our own sideways motion.
Right. But the auditor AI points out that if you look at the vertical path, the sideways arm from that God's eye view, it's that hypotenuse again. The source gives those coordinates again. The vertical mirror moves from 0, 10 to 110. The light has to travel the square root of 10 squared plus 1 squared. It has to travel the square root of 101.
Which is roughly 10.05. It's not 10.
Exactly. It's not 10. It's 10.05. The light traveled farther. The source claims that traditional diagrams just draw the path as a vertical line of distance 10, completely ignoring that extra 0.05 of distance caused by the lateral motion. And because they ignore it in the drawing, in the geometry, they're forced to account for it by fudging the time variable.
So the argument is that the interference fringes are stable, not because light speed is magical and time is flexible, but because the actual geometric path differences naturally cancel out or stabilize in a way we haven't properly calculated.
Or rather, that the phase difference we measure is real, but we interpret it as no motion because we refuse to acknowledge the phase 3 geometry. We assume the path was 10. It was 10.05. If we just acknowledge it was 10.05, we wouldn't need time dilation to explain the delay. The delay is just more distance.
This really brings up a massive conceptual shift. It's moving away from an observer-centric view of the universe to something more like a light-centric view.
Yes, and that's part 4. The paradigm shift. The source uses this great analogy involving Galileo and Newton, the apple analogy.
Oh, I think I know this one. Galileo looked at a falling apple and said, "The earth is fixed. The apple falls to the earth." It's an egocentric, observer-centric view.
Right. I am standing still on the ground, therefore the apple is doing all the work. But then Newton came along and said, no, wait. Actually, the apple and the earth are both pulling on each other. They're moving toward a common center of gravity.
Newton acknowledged the interaction. He stepped outside the observer's frame of reference.
And the source argues that modern physics is still Galilean when it comes to light. We assume we, the measurement device, the lab, the Earth, are the fixed coordinates. We act like we're at the 0, 0 point of the universe.
And the light is just something that's happening to us.
Exactly. But the Zainanchep model says, no, we're moving. The light is moving. We're all just objects careening through this light history map. We need to step out of our own shoes and see the interaction from that God's eye view.
And this must be what explains why the independent space-time auditor, that AI you mentioned, switched sides so dramatically. You mentioned a hierarchy of observation.
Yes. This was the core of the AI's logic for its 98% conversion. It described 3 distinct levels of observation. Level 0 is the dummy doll.
The dummy doll.
Yeah. Imagine a crash test dummy sitting in the lab. It assumes it is completely static. It sees everything happening relative to itself and itself alone. The source says that's us most of the time.
Okay, that makes sense. Level 1.
Level 1 is the camera eye. This is a bit more sophisticated. It accounts for geometric aberration. It knows that things could look distorted because of speed and perspective, but it's still fundamentally rooted in its own frame.
And level 2.
Level 2 is the God's eye view, the light history map. This view sees the absolute paths of the photons and the absolute path of the observer all moving through the same coordinate space.
And the AI concluded that level 2 is the superior, more accurate model.
It did. The AI argued that the phase 3 model, using the simultaneous equations from the level 2 perspective, is the one that satisfies Occam's razor. It eliminated the need for these extra complicated concepts, like time warping. The AI basically asked, why invent a warping universe when simple, predictable motion explains the data perfectly?
It's a very powerful application of Occam's razor, but the sources go even further than that, don't they? They connect this to quantum mechanics.
Oh, this is the wildest part of the whole stack, the probability insight. The source directly connects this geometric error to Schrödinger's cat and the idea of electron clouds.
Okay, but that's a leap.
Wow.
How do you possibly get from the Michelson-Morley experiment to Schrödinger's cat?
The source claims that concepts like probability and uncertainty are just symptoms of missing information, specifically missing information about our own speed.
Unpack that. That's a huge statement.
Okay, so we're trying to measure the position of an electron, but we, the measuring device, the scientists, the entire lab, are moving through the universe at some massive unknown velocity. Because we don't calculate our own absolute motion in space, we don't do the phase 3 calculation, we can't predict exactly when the collision, which is the measurement, will happen.
So we can only predict a range of possibilities. A smear. A cloud of probability.
We call it quantum probability, Heisenberg uncertainty principle. But the source says it's just ignorance. It's a fudge factor for data we don't have. If we knew the exact trajectories of both the electron and our measurement device, if we were using that God's eye view, there would be no uncertainty. The electron is there. We just don't know exactly where we will be when we try to touch it.
That is a radical claim. It suggests that the inherent weirdness of quantum mechanics isn't a fundamental property of nature at all, but a fundamental limit of our Galilean observer-centric perspective.
It turns spooky action at a distance into just fast-moving geometry we forgot to track.
You know, if you accept the initial premise that we have fundamentally ignored the observer's motion in our baseline equations, it really does create a domino effect. It challenges special relativity, and then it goes on to challenge the foundations of quantum mechanics.
It challenges the fantasy of the stationary observer. That's the exact phrase the source used. We want so badly to be the center of the universe, the unmoving, fixed point. But we aren't.
It's humbling. And it's exactly the kind of critical thinking we need in science. Even if you don't buy the whole package, the exercise of asking, wait a minute, did we draw the triangle right, is invaluable.
Absolutely. So let's wrap this up with a summary of the key takeaways from this whole deep dive.
Okay. First, the standard interpretation of the Michelson-Morley experiment relies on a textbook diagram that the sources claim is lazy. It connects points in time without properly accounting for the lateral motion that happens in between.
Second, if you actually solve the geometry with simultaneous equations, what they call phase 3, you find that the light's path is physically longer. And this extra distance fully explains the time delay without needing to warp time itself.
And third, the auditor AI concludes that acknowledging the observer's own motion is the key to a simpler, more unified physics. It eliminates the need for time dilation and could even potentially explain quantum uncertainty as just a lack of data about our own movement through space.
It is a lot to chew on. But I want to leave you, the listener, with this one final provocative thought that comes from the source material.
Go for it.
The source asks, are we ready to abandon the fantasy of the stationary observer? I mean, really think about that. Every time you look at a physics problem, or even just look out the window, you instinctively assume you are still. But you are on a rock spinning at 1,000 miles an hour, which is orbiting the sun at 67,000 miles an hour in a galaxy that is shooting through the void at 1.3 million miles an hour.
We are careening through the universe at unimaginable speeds. We are anything but stationary.
So if we admit that we really truly bake that fact into our math from the very beginning, does the mystery of the universe dissolve? Does the warping of time and the fuzziness of atoms just straighten out into simple, albeit incredibly fast-moving geometry?
It definitely makes you want to open up an old textbook and look at those diagrams with a very fresh and maybe a very skeptical eye.
That is exactly what we want you to do. Don't take the diagram for granted. Check the angles. Question the assumptions. And remember, sometimes the biggest tricks are hidden in the simplest drawings. Thanks for diving deep with us today.
Keep questioning.
We'll see you on the next one.